All right, so today we are going to dive deep into something I think a lot of our listeners have probably thought about.
Yeah.
How do we actually understand what a computer program, what code really means?
That's right. It's a fundamental question. How do we assign meaning to these sequences of symbols?
Yeah, and on the surface it seems like, okay, well, it just does what it does, but is there a deeper way to understand the meaning? A more rigorous way?
Definitely. And there are actually, formal ways to think about program meaning, not just in terms of what we observe, but through rigorous mathematical frameworks.
Okay, so there's like almost a philosophical side to this as well, right? It's not just about the practicalities of coding, but about the very essence of what code is.
Absolutely. And that's what makes this deep dive so interesting, this intersection of the practical and the theoretical, the philosophical even.
So where do we even begin? I mean, how do we start to formally understand what a computer program means?
Well, there are two main approaches we'll explore. One is called operational semantics, and the other is denotational semantics.
Operational and denotational.
Right. Think of operational semantics as describing the step-by-step execution of a program. It's like a recipe, detailing what happens at each stage of the computation.
Okay, so it's like the program's execution unfolding in time, step by step, like a process.
Exactly. Now, denotational semantics takes a more abstract approach. It interprets programs as mathematical objects, giving them meaning in a mathematical world.
So one is about the process of running the code, and the other is about the object it represents mathematically.
Precisely.
Okay, so now if we've got these two different ways of looking at meaning, it naturally leads us to ask, when do two programs have the same meaning?
Right. When are they equivalent?
Yeah, like if we can understand them operationally and denotationally, when can we say, these two programs, even though they might look different, they essentially mean the same thing?
And that's a crucial question. That's where the concept of full abstraction comes in. It's a property, a benchmark, you might say, where our operational notion of program equivalence, what we observe happening when programs run, perfectly aligns with our denotational notion, the mathematical interpretation.
So full abstraction is this ideal state where the two perspectives, the doing and the being, if you will, perfectly match up.
Exactly. It's like a perfect harmony between the practical and the theoretical. And the quest for full abstraction has driven a lot of research in programming language semantics.
So it's not just a theoretical curiosity. It has practical implications for how we understand and design programming languages.
Absolutely. It helps us reason about programs, about their correctness, about their equivalence. It gives us a solid foundation for building reliable software.
And it's also, I imagine, relevant to the philosophy of computer science, to the very nature of computation itself.
It definitely is. I mean, full abstraction touches on fundamental questions about meaning, about observation, about what constitutes an observation in a computational system.
Yeah, what does it even mean for two programs to be indistinguishable? It gets really deep really quickly.
It does. And some thinkers, especially those with a philosophical bent, have drawn connections between full abstraction and the philosophy of language, the ways we assign meaning in any kind of symbolic system.
Fascinating. So we're aiming to understand how programs mean, the relationship between their execution and their mathematical representation, and this ideal of full abstraction where those two perfectly agree. It's a tall order.
It is. But it's a journey worth taking. And it all starts with understanding some key concepts.
Okay, so let's lay the groundwork then. Where do we begin?
A great place to start, especially when explaining this to, say, a philosopher, is with the concept of compositionality.
Compositionality. It sounds like the idea that the meaning of a complex whole is built up from the meanings of its parts. Like if you understand the individual words in a sentence, you can understand the meaning of the whole sentence.
Exactly. It's about understanding the meaning of something by understanding the meaning of its constituents and how they're put together. And in denotational semantics, compositionality is a key principle.
Okay, I see. So for denotational semantics to be, I guess, good in a sense, it should be compositional.
Right. That's generally considered a desirable feature because if a semantics is compositional, it means that the meaning of a program is a function of the meaning of its subparts and how those subparts are combined.
Makes sense. It brings a kind of clarity and structure to how we understand programs.
Right. It allows us to break down a program into smaller, more manageable pieces, understand those pieces, and then compose those understandings to grasp the meaning of the whole program.
So it's not just about assigning arbitrary meanings to programs. It's about doing it in a way that respects the structure of the program, the way it's built from smaller components.
Yes.
Now, you mentioned before that we can talk about program equivalence from both operational and denotational perspectives. Let's unpack that a little. What does it mean for two programs to be equivalent operationally?
So operationally, two programs are considered equivalent if they have the same observable behavior. That means that no matter how you run them, no matter what inputs you give them, they'll produce the same outputs.
So it's about their external behavior, what we can observe from the outside.
Exactly.
And what about denotationally? How do we determine equivalence from that perspective?
Denotationally, two programs are equivalent if they have the same mathematical interpretation. Remember, in denotational semantics, we're assigning mathematical objects to programs. So if two programs map to the same mathematical object, then they're denotationally equivalent.
Okay, so it's about the underlying mathematical meaning being the same, even if the programs themselves might look different.
Exactly.
Now, we've talked about these two notions of equivalence, and we've talked about this ideal of full abstraction. Can you remind us how those connect?
So full abstraction is the property where those two notions of equivalence perfectly coincide. If two programs are observationally equivalent, then they're also denotationally equivalent, and vice versa.
So it's like a two-way street. Same behavior means same mathematical meaning, and same mathematical meaning means same behavior.
Exactly. And that's what makes full abstraction so powerful. It means our mathematical model, our denotational semantics, captures precisely the observable behavior of programs.
Okay, I think I'm starting to grasp the significance of this, but before we delve deeper into full abstraction, you mentioned a concept called computational adequacy. How does that fit in?
Ah, yes, computational adequacy. It's actually a weaker requirement than full abstraction. Essentially, a denotational semantics is computationally adequate if it correctly predicts the outcome of program executions.
Okay, so it's about getting the basic results right. If a program computes the number 42, then our mathematical model should also point to 42.
Exactly. It's a fundamental sanity check. Our model should at least agree with the program's observable output.
And full abstraction is about something more.
Right. Full abstraction goes further. It requires that not only do the final results match up, but also that any two programs that behave the same in all possible contexts have the same denotation.
Ah, so it's not just about the final answer. It's about the entire process of computation being reflected in the mathematical model.
Precisely. And that's where things get tricky. Achieving full abstraction can be surprisingly difficult.
And this difficulty leads to what's often called the full abstraction problem.
Exactly. And a classic example of this problem arises in the context of a language called PCF.
PCF, what's that?
PCF stands for Programming Language for Computable Functions. It's a simple yet powerful language that's been a kind of testing ground for semantic theories.
So it's like a simplified model of a real-world programming language, but one that still captures many of the essential features.
Exactly. PCF has basic types like natural numbers and booleans, functions, conditional statements, and a way to define recursive functions.
Recursion, that's where a function calls itself, right?
Right. Now, PCF usually has a call-by-name operational semantics. This means that when you call a function with an argument, the argument is only evaluated if it's actually needed.
Okay, so it's a bit lazy in a way. It only does the work if it absolutely has to.
Yeah, you could think of it that way. And this lazy evaluation strategy has some interesting consequences when we consider programs that might not terminate, that might run forever.
Ah, like an infinite loop.
Exactly. We call those programs divergent. And in PCF, we can actually define a term, often denoted as omega, that represents this idea of divergence.
Omega, so it's like a symbol for a computation that never ends.
Precisely. And this concept of divergence can affect the behavior of other operations. Let's take Boolean operations as an example.
Okay, like AND and OR.
Right. Normally, true or false would be true. But in PCF, if the second argument to OR is omega, the divergent term, the result might still be true because the evaluation might stop as soon as it sees the true and never actually try to evaluate omega.
So the lazy evaluation, the call by name, changes how we think about the meaning of even basic logical operations when divergence is involved.
Exactly. And this is where things get really interesting.
Okay, I'm intrigued. Tell me more.
There's a function called parallel OR, often written as core, that behaves like regular OR on standard Boolean values, but it can also handle divergence in a way that's crucial for the full abstraction problem.
Okay, so how does this poor function work?
Well, with poor, even if one of the arguments is divergent, is omega, if the other argument is true, the result is still true. It's like it can evaluate both arguments simultaneously in parallel, and as soon as one yields true, it returns true, regardless of whether the other one ever finishes.
Interesting. So poor can somehow see past the divergence if there's a true hiding in there somewhere.
Exactly. And here's the catch. While poor makes sense mathematically, you can't actually define a PCF program that computes poor because of PCF's sequential nature.
So PCF, with its call-by-name evaluation, can't truly do parallel computation.
Precisely. And this is where the full abstraction problem arises. When we try to create a denotational semantics for PCF, a mathematical model that assigns meaning to PCF programs, we often use structures called domains.
Domains, what are those?
Domains are mathematical objects, kind of like sets, but with more structure, that are used to represent the possible values of computations. They have this notion of a bottom element, which represents divergence, the undefined value.
So domains allow us to talk about not just well-defined values, but also the possibility of a computation never ending.
Exactly. And for function types in PCF, the domains consist of continuous functions, functions that preserve a certain kind of smoothness when going from arguments to results.
Okay, continuous functions. I vaguely remember that from calculus. It's about functions that don't have any sudden jumps or breaks, right?
Right, something like that. In the domain setting, continuity has a slightly more abstract meaning, but the intuition is similar. It's about preserving certain limits. And these continuous functions are crucial for interpreting recursion in PCF.
So we have domains and continuous functions, and we use them to give a mathematical meaning to PCF programs.
Exactly. And this standard denotational model, using domains and continuous functions, is computationally adequate for PCF. It means that if a PCF program computes a certain value, the model will assign that same value to the program.
So it gets the basic results right, but it's not fully abstract.
Right. The problem is that this model is too powerful in a way. It can distinguish between PCF programs that are operationally indistinguishable.
Wait, how can that be? I thought if two programs behave the same, they should have the same meaning.
That's what we'd like. But the standard model can see a difference based on how the programs would interact with this hypothetical poor function, even though poor is not definable in PCF itself.
Ah, I see. So the model is taking into account things that PCF can't actually do.
Exactly. It's like the model is considering a wider range of computational possibilities than what PCF allows.
So the standard model fails to capture the inherent limitations of PCF's sequential nature.
Right. It's not fully abstract because it can differentiate between programs that are, for all practical purposes, within PCF the same.
Okay, so what have researchers done to try to address this problem, this mismatch between the model and the language?
Well, one approach has been to develop more sequential denotational models that better reflect the step-by-step nature of PCF's computation and exclude things like poor. For example, there's a model based on the concept of stable functions, which are functions that depend on a minimal amount of information from their inputs.
So stable functions are a way to capture the idea that a computation shouldn't rely on information that might be divergent, might never become available.
Exactly. And there's also been a lot of work on sequential functions, functions that have a specific order in which they need to access their arguments. And a key result is that for functions over simple types like Booleans or natural numbers, a function is sequential if and only if it can be defined by a PCF program.
So sequentiality really captures the essence of what PCF can do.
Right. And other approaches have focused on modeling the dynamics of computation more directly, using ideas like concrete data structures or sequential algorithms.
It sounds like there's been a lot of effort to find a model that perfectly aligns with PCF's behavior.
There has been. But ultimately, the breakthrough came from a rather different direction. Game semantics.
Game semantics. Now that sounds intriguing.
It is. Game semantics takes a very different perspective. It models the meaning of a program as a game played between two players, the program and its environment.
A game, like a board game.
Not quite. Think of it more like a dialogue, an interaction where the program and the environment exchange information.
So it's not just about what a program computes, it's about how it interacts with its surroundings.
Exactly. And game semantics captures this interaction as a sequence of moves in a game. The environment might make a move by requesting some input, and the program responds by providing that input. Or the program might make a move by outputting a value, and the environment observes that output.
It's almost like the program and the environment are having a conversation, exchanging questions and answers.
That's a great analogy. And in this game semantic view, the meaning of a program is not just a static mathematical object, It's a strategy for playing this game.
A strategy. So it's a plan for how to respond to any possible move the environment might make.
Precisely. And game semantics provides a very precise and elegant way to define these strategies and to compose them, which is essential for understanding how complex programs behave.
Okay, so instead of mapping programs to fixed values, we're mapping them to these dynamic strategies for interaction. That's a pretty big shift in perspective.
It is. And the really cool thing is that game semantics has been incredibly successful in providing a fully abstract model for PCF.
Really? So they finally cracked the problem.
They did. And the key insight was to impose certain constraints on the strategies, constraints that reflected the sequential nature of PCF. For example, there's a notion of innocent strategies, which essentially means that the program can't remember past interactions, it can only respond based on the current state of the game.
So it's like the program has no memory, it lives in the moment.
Right. And this restriction to innocent strategies is crucial for capturing the behavior of PCF, which doesn't allow for side effects or stateful computations.
So game semantics, with these carefully chosen constraints, finally achieved full abstraction for PCF.
Yes, it did. And it opened up a whole new world of research, applying game semantics to more complex languages and features.
That's incredible. We've gone from this basic question of what does a program mean to this whole journey through different semantic approaches, culminating in this elegant solution using game semantics. It's been quite a ride.
It has. And I think it highlights the beauty of computer science, how it combines rigorous mathematics with deep conceptual questions about meaning and computation.
For our listeners who are, say, more philosophically inclined, what would you say is the key takeaway from all this? Why should they care about full abstraction or game semantics?
Because these ideas, while technical, touch on fundamental questions about how we understand meaning, how we reason about systems, and how we model the interaction between an agent and its environment. Game semantics in particular offers this very elegant framework for thinking about computation as a kind of dialogue, a process of exchange and interaction.
That's a beautiful way to put it. So it's not just about the nuts and bolts of programming, it's about these deeper philosophical questions about knowledge, meaning, and interaction.
Exactly.
For our listeners who are now eager to learn more about game semantics, where would you point them?
Well, a great starting point would be the Stanford Encyclopedia of Philosophy entry on game semantics. It provides a very accessible overview of the field and its connections to logic and computer science.
Perfect. Well, thank you so much for guiding us through this fascinating landscape of program meaning and full abstraction. It's been a true deep dive.
My pleasure. Always happy to talk about these things.
And to our listeners, keep pondering those deep questions.